Alright, welcome back, guys. In this video, I want to go over exploration 7.3.1. It's called In a Perfect World. I know last exploration we went over experimental probability and we kind of played around with the idea of having infinite amount of trial experiments, or how could we do that, because we saw that the more trials we had, the more fair of an outcome we were to get, right? A closer outcome to a fair outcome we got. Like, it was better to do 10 trials as opposed to one, or 100 trials as opposed to 10. So in this exploration, we want to really look into the idea of, okay, how do we think about in a perfect world, right? Not 10, not 100, not 1,000 trials. How can we get to like a accurate prediction, which is called a theoretical probability, right? So in this whole exploration, we're going to be talking about a theoretical probability and how we can calculate it, for our example, using heads and tails. And the way we're going to do that is by using a binomial probability distribution, right? So this works because there's only two outcomes, heads or tails. Flipping a coin, yes or no, right? So like heads or tails, we could use binomial distribution. Any other one that has only two outcomes, experiment with two outcomes, we could also use binomial distribution. So I know a lot of this is really looking complicated, but I did my best to kind of break down the formula for us to use. And there's a lot of notes and activities. I also attached like videos from Khan and Desmos to kind of go a little more into detail than we did here. But we didn't have a lot of time to go over this. I don't want to. I didn't want to throw it all at y'all, especially with me not being there to explain it in person. So let's go ahead and get started. Sorry for the long introduction. We're gonna look at the same situation here, but instead of doing experiments, we're going to use our binomial probability formula. What this formula does, it's ugly, it looks complicated, but it actually calculates probabilities for us. So it looks really hard and complicated, but I give you what each of these variables represent. So n is the number of trials, r is the number of specific events that we want to obtain, p is the probability that that event will occur, and q is the probability that that event will not occur. Okay, so let's go ahead and get started here. We want to first start off by answering question 1. What is the value of n? Well, if I look here, n is the number of trials. And this is where it gets complicated. It's like, okay, so how many trials do we want to run, right? How many times do I have to flip the coin? Well, I'll give you a hint. When we're talking about the number of trials, we're actually talking about the total number of times until this game comes to an end, until this decision is calculated, right? So in our case, what is the total maximum number of times you'd have to flip the coin for this game to end? Some people say 1 because then Mr. DeLeon wins, but that's not the maximum, right? What's the maximum number of flips we can have? We think about it, well, that would be when Mr. Bustamante wins, right? So the maximum number of flips would be 4 flips, because if I flip the coin 4 times and got 4 heads, right, that would determine the end of the game. So 4 flips. So 4. So I'm just gonna put n is equal to 4, because that's the number of times Mr. Bustamante needs a hit. Again, if we had any less than that, Mr. DeLeon would probably win, because he would hit that tails on his first try. Okay, so for question number 2, what is the value of r in the formula above? Well, it's very similar to n, so r should just be 4, because that's the number of times that I need to, or how many points Mr. Bustamante needs to win the game. Moving on to question 3. What is the probability of heads to be flipped? This one's not too bad. We know since it's a coin and it's fair, the probability P is just 50%, right? 50% heads. So again, we're tackling this probability problem from Mr. Bustamante's perspective. It could also be done from Mr. DeLeon's, but we're just going to look at my perspective first. That's why we're calculating the probability of heads, and we're asking these questions about Mr. Bustamante. What is the value of Q in the equation above? So Q is the probability that heads is not flipped, right? So the event will not occur, because the event we're talking about is probability of Bustamante winning, right? So that's whenever I say event up here, because it could be confusing, that's the probability of me winning. So the event is Mr. Bustamante winning. So the probability that heads will not be flipped, that would just be tails, right? So Q would be 50% as well. So we're going to put all this into Desmos and go ahead and calculate Mr. Bustamante's actual probability of winning, my theoretical probability. So I'm going to plug it all in. I could plug it in by hand for 4 factorial divided by 4 factorial times n minus r factorial, which is 4 minus 4 factorial, times, let's see, probability of winning is 0.5 to the 4 times 0.5 to the 4 minus 4. Okay. I went ahead and put this into Desmos, and I ended up with 0.0625. Right, so 0.0625, which is about 6%. So we can really think about this. How does this compare to our answers in the previous expressions? When I personally did it, I got 10%, so that wasn't very far off. You know, y'all might have even been closer to me depending on your experiments and how they ran, right? But the idea is the more experiments we run, the closer to this percentage, that this theoretical probability, right, that we're going to get, right? So this theoretical probability is, in a perfect world, this should be the outcome, right? So in the most fair way, by calculating theoretical probability, no luck, just like fairness and odds and all, I should win 6% of the time. So that means to me I should get 6% of that pot. So 6% of that pot goes to Mr. Bustamante. We want to do example number 6, or question number 6 now. It says, based on our example number 5, what's the probability Coach De Leon wins? So I gave y'all a hint because I didn't want to make it too hard on y'all, but I'll go over it the theoretical way. So we want to set up that binomial equation again, right? We want to think about how the numbers are going to change. So this time our number of trials is still going to be 4 because that's the maximum number of trials to have. And we can calculate, okay, well, how many times does Mr. De Leon have to flip the coin to win? Just once, right? Tails. And then we have our equation 4 minus 1, all right? So I'm just going to simplify these out. 3 factorial. And then we just do the times 0.5 to the first power, because that's the coins we want. And then again, times 0.5 to the 4 minus 1, which is 3. So there's kind of a pattern here. This number here, your r is always going to go here, and then your n minus r will always go there, right? So those are the same equations. I went ahead and put this into Desmos, and I ended up with 0.25, so 25% chance that he's going to win flipping one coin, right? Hitting tails once. So that's a 25% chance. Now we have a question. Okay, so why doesn't this add up with the 6% to equal 1 if that's the hint I gave you? Well, because Mr. De Leon can also win if he hit 2 coins in a row, right? Or 3 coins, because we're talking about 4 trials happening here. So we have to add up the probabilities that if, like what in theoretical, right? Even though we know he won the game after 1, theoretically, we have to calculate every single thing. This is where this method of calculation kind of becomes perfect, because now we're considering every single option, even options that we wouldn't consider, because like in an experiment, once I hit 1 tails, right, I'm done with the experiment. I'm done. He won already. But mathematically now, to calculate it theoretically, we have to calculate, okay, well, in those 4 trials, what's going to happen, right? So it doesn't affect our answer too much. So this is kind of just 1 tails, right? Like the probability of 1 tails coming up. Then we can do the 2 tails, and we'd have to go on 3 tails and 4 tails, right? And so we're going to calculate all of those up, and our equations is kind of just stays the same a little. It changes a little bit. So we still have 4 trials. This time r is going to be 2 tails, right? And then 4 minus 2 is 2. And then we have 0.5. Again, we're going to match up these numbers. So 2 times 0.5, 2. And when I went ahead and did that, I got 0.37. Oh, so this shouldn't be 0.25%. It should just be 25%. I apologize. And this one, I ended up putting in Desmos, and I got 0.375, which is 37.5%. Okay. And then 3 tails. So we're going to go ahead and do that one next. So this was 2 tails. Here's 3 tails. We had 4 trials. We want 3 tails this time. 4 minus 3 is equal to 1. 0.5 times match them up. 3 times 0.5 times 1. And Desmos told me that that was 25%. Okay. And we got one more, 4 tails, right? So I'm going to bring this one down here to the bottom. So 4 tails. So 4 trials, 4 tails. 4 minus 4 is 0. And then we're going to match these up. 0.5 to the 4th power, 0.5 to the 0th power. And Desmos told me that that's 0.0625 or 6.25%. Now, Mr. DeLeon can win in all of these cases. So what we're going to do is we're going to add them all up. And we end up getting 93.75% chance of Mr. DeLeon winning. That's very close to our 90% we got in exploration 7.2.1. So I just want to spend, I know this seemed complicated. It's good because in this theoretical model, right, we don't care if he just wins the game. We got to consider all possible outcomes. So you may say, well, why was Mr. Boost so easy, right? Like what made his like probability calculation just one time? Well, because for Mr. Bustamante to win, he needed all 4 of those heads, right? There was no other way he could win. Out of those 4 trials, he needed all 4. And this makes sense because if you add 93.75% to our previous example, our answer in example 5, you end up with a total of 100% or 1. Okay. So there's a lot of ways you can, in lieu of doing these calculations, I just wanted to show y'all a little more practice with it. You can actually just do 1 minus the answer in question 5 and you'll get the complement probability kind of, right? So what we want to do now is answer question 7, and I'm going to leave this to y'all because you have to compare them. Based on my comparisons, we had in 7.2.1, we had 10%, right? And 90%. And now in this exploration, 7.3.1, we had 6.25% and 93.75%. So these are really, really close, right? And again, that's because in exploration 7.2, we only did 20 trials. But imagine what would happen if we did 100, right? I didn't want to wear y'all out. But the more trials we would have done, the closer we would have got to these theoretical probabilities. Okay, guys? So hopefully that helped y'all out. It's kind of a cool little exploration, a way for us to pass time in quarantine, me and Mr. DeLeon. So y'all go ahead and have a great weekend, and then we'll see y'all next week. Please don't forget, even though you went through these videos, make sure you click on that Google form and submit your answers so I could give you some credit. Appreciate everything you do, guys.